In the last section, we looked at finding antiderivatives numerically and graphically. And in this section, we're going to look at finding antiderivatives analytically. All right, so given a function, a formula for a function, we're going to learn some rules for finding the antiderivative as a formula, right, as a function. Okay, so, but before we do that, let's take a look at these derivatives. Okay, so we have in example 1, we're given some functions and we're asked to find the derivative of each function. And so the first one is just x squared. So we can find the derivative of that easy enough. The derivative of x squared is 2x, right? The derivative of x squared plus 5, right? The derivative is what? It's going to be 2x, and then the derivative of 5 is 0. So the derivative is 2x again. X squared minus 289. All right, well, the derivative of x squared is 2x again, and then when we take the derivative of this constant, it's 0, right? So our derivative is still 2x. In this last one, we have x squared minus pi. Now, pi is a constant, right? It doesn't vary with x, so we get the derivative of x squared is 2x, and the derivative of the constant is 0. Okay, so notice all of these functions have a derivative of 2x. And if we take the derivative of x squared plus some arbitrary constant, c, right? If c is a constant and we take the derivative of it, that's going to be 0. So no matter what c is, no matter what c, whether it's positive or negative, whether it's pi or e, we're going to get 2x, right? Because the derivative of that constant will be 0. So now, what is the antiderivative of 2x? So what we mean by that is what function has a derivative of 2x? What function has a derivative of 2x? Well, I'm going to call this capital F of x because it's the antiderivative. And so the antiderivative of 2x has to be x squared plus some constant c. Any constant would be fine, right? And we'd still get a derivative of 2x. So because the derivative of x squared plus c is 2x, then the antiderivative of 2x has to be x squared plus c. So this brings us to the idea of an indefinite integral. All right, so if capital F is the antiderivative of lowercase f, okay, so that means that capital F prime is f of x, right? So let me write this down. F of x is the antiderivative, is the antiderivative of f of x, okay? We use the integral symbol, this summa, to indicate that we want to find the antiderivative of the function that follows. So we want to find the antiderivative of this lowercase f of x. And the antiderivative, we're going to use capital F of x to indicate the antiderivative, right? This is an antiderivative. Capital F of x is an antiderivative, and then we add an arbitrary constant to it, right? Because the derivative of the antiderivative has to give us back this lowercase f of x, right? And so if we add a constant, the derivative of the constant is 0. So when we have capital F of x plus this arbitrary constant, it represents a whole family of antiderivatives of the lowercase f of x, right? So so we get a whole family of functions. All right, I'll meet you in the next video for the next example.